Howdy folks, good afternoon. I'd like to discuss a little topic which has to do with quantum mechanics. As you know, I'm also discussing some scientific topics, and this time I want to discuss about the measurement problem. They've done some experiments with a measurement problem with the young experiment where particles are shot at a two-slit experiment thing, and they see a typical pattern of the particles being deposited on the screen. Well, I like to talk about this subject. I like and discuss what happens over there and how to clarify what I'm going to say, what I'm about to say. A couple of years ago, I wrote 2 papers about it. Here they are. 2 different papers about it. In one of them, I discuss how you can verify what I'm saying. Two slits, wave function collapse, and the measurement problem. What happens, and is there a real problem? Is this one? Top one. And collapse or not to collapse, that is the question. How to verify or reject the interaction of a wave function with a microscopic detector in order to test wavelength contraction instead of a collapse. That's the second one. Yeah, I wrote 2, and I also try to look contact with. There is on YouTube, you can see it, and it's a nice thing, I think. I think it is done by IBM, if I recall well. Let me see, I checked it here. I put it here. Okay, well, it doesn't say that much. No, but okay, I'm going to mention it. There is a movie on YouTube which is called A Boy and His Atom. That is, I think it was IBM did that in Germany. They made a little movie about with moving atoms, individual atoms, and they made a movie out of that. They made individual pictures by moving atoms around, and just to make a movie at atomic level, and a boy and his atom. A boy and his ball, atom ball. And at that level, we have to start thinking in wave terms of waves. And that's what I'm going to discuss, and also I'm going to show you something. Okay. The old-fashioned, let me take a pen, old-fashioned, the young experiment, the measurement problem. I'll take the board a little closer so you can see it. Okay. What's happening? We have a particle gun. It doesn't matter whether it is electrons or photons or bigger particles, buckyballs. It doesn't matter. The principle remains the same. Now, what you see in the original two slits, you get a diffraction pattern. Yeah? But if you, without a detector, without somebody to observe, but if you put a detector, represented by this big eye, and all of a sudden, this reduces to 2 points. But the question is why? What happens? Well, and that's what I'm going to discuss. What happens is that you put the particles that come here through the slits in contact, basically in entanglement with a detector. And a detector is quantum mechanically spoken, a very big object. That means that the deBroglie wavelength of that object is very, very, very small. Now, if you are measuring, you are bringing the particle that is moving through the slits either as a particle, either as a wave, it's changing its wavelength due to the interaction with the detector. The detector has a very small wavelength, so the particle is becoming, you are integrating it, so to say, system-wise into the detector system, quantum mechanically button. That means that also its wavelength alters to very, 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 very small wavelengths. And then it starts behaving more classically. Yeah, like here. This is purely quantum mechanically. You can see this is also quantum mechanically, but since the wavelength has changed because you're entangling it with the observer, and the observer has a very small wavelength, the wavelength shrinks. And then it behaves just like tennis balls. I mean, then you get two blobs where the particles end up because you made the wavelength very small, and thus they end up in two blobs because you entangled it. There is a process of entanglement when you observe. When you observe, you entangle it with the observing instrument, so to say. Now, this leads so-called to a measurement problem, a collapse of the wave function. No, it doesn't collapse. It shrinks. It doesn't collapse. It becomes smaller, but there is still a wave function. Yeah. So basically, this problem is this thing is very simple. What happens is you start out with wave function 1 here. Now, wave function 1. And here you have a wave function, here it's unaltered, so here it will remain wave function 1. But here it starts out as wave function 1, and here, because of the interaction with the detector, it becomes wave function 2. Which resembles, which is in the order of magnitude of this is to B, and this is to A. And these wave functions, they resemble in wavelength, in deBroglie wavelength. They're in the same order of magnitude because you are entangling, due to the observing interaction, you are entangling them, you are making them one whole system. So you can designate them as wave function 2A of the original observing instrument and wave function 2B, which has the same order of magnitude of deBroglie wavelength as the detector has. Now, there's to verify this idea that I postulated a couple of years ago and published it on what was it, ResearchGate I did, but it was removed, and later on academia, academia.edu, you can find those papers that I originally wrote in 2018, I remember, and over there you can solve to check this out if I'm correct, yes or no. I mean, I may be wrong, but to check it if I'm wrong or not, what you can do is downsize your detector in such a way that you create here a wave function which has a measurable wavelength. And so what you can do is, and that's why this I is very small here, very small I, almost a dot. So there is an interaction with the detector. So due to that, the wave function goes from wave function 1 to wave function 2, whereby the wavelength, the deBroglie wavelength of 1, this here, is way much bigger than the deBroglie wavelength of the particle after detection. Yeah? And what you can do is make the detector incredibly smaller, so that the wave function of the detector is way much smaller, but still detectable. I mean, of course, that's a technical challenge. I agree. But if you make the detector deBroglie wave function way much smaller and in the area of atoms and or molecules, if you make a detector composed of kind of molecules, then the wave length, the deBroglie wavelength, also shrinks. And what happens then, if you put then the young experiment and you put it in such an arrangement, then of course if you detect it normally, you will find two blobs, most probably. But if you put then behind it, in one of the position of one of those blobs, another grid, a two-slit grid, then you again will find a characteristic pattern that resembles this one, but smaller. Why? Smaller because the wavelength have changed. Yeah, it's still quantum mechanically. Also, this is quantum mechanically. That the quantum mechanic thing is not changing. The only thing that changes is the deBroglie wavelength of the particle. That's the only thing that changes. And you can verify this, or if I'm wrong, I mean, let's be honest, as a scientist you have to be honest and also accept that if you're wrong. So if I'm wrong, then you will never ever find this double slit pattern with a shrunken down detector. But in order to test this, so you have to make smaller and smaller detectors if possible. And then if I'm correct, if this idea or this theory is correct, you will eventually find a two-slit pattern in the second stage after detecting it, if I'm correct. And if not, well, then I'm wrong. It's simple. Yeah. Well, those papers deal about that, and what I did, I contacted some years ago. The camera's close to falling. That's what I mean. Yeah. Back. Yeah. Well, I contacted IBM in Germany with my papers and with this idea, and well, so far I didn't hear anything about it. And that's why I make this video, because I like this idea to be tested, to whether I'm right, whether I'm wrong. And so that's why I made this explanation, to explain it in a video, and to explain what the basic idea is. Make detectors as small as you can, and the smaller the better, because then this effect of deBroglie wavelength shrinkage you will detect. It's not a collapse. It's always named a collapse. What happens is that the wavelength collapses. No, it shrinks down. And if I'm correct, then it only shrinks down. The whole thing remains quantum mechanically correct, but it shrinks down. The only thing that's happened is that the deBroglie wavelength shrinks down. Okay, well, that's basically what I want to share, and thanks for watching, and see you next time.